Okay, as we mentioned last week, there are several different gas laws that we will be working with in this unit. Last week, we focused on Dalton's law and Boyle's law. And today, or this week, we will be looking at Charles' law and Gay Lussac's law. Just like in the previous two laws from last week, make sure your pressures are always in the same unit. If they are, great. If not, then you're going to have to get one pressure to be the same unit as the other one using our various conversions. What's different this week is temperature. Both of these laws have temperature, and in order to use these gas laws, your temperature has to be in Kelvin, not the Celsius scale, in the Kelvin scale. In the Kelvin scale, absolute zero is 0 Kelvin. That's the coldest temperature that is theoretically possible. The way we convert Celsius to Kelvin is we add 273 to whatever temperature we have in Celsius, and you'll see some examples of that. So to start off, Charles' law says the volume of a gas is directly proportional to its temperature when you're in Kelvin. So volume of a gas is proportional to temperature. We saw that last week. When the temperature went up, the volume went up. When the temperature went down, the volume went down. So if we look at this first problem, it says, suppose a gas has a volume of 6.8 liters. 6.8 liters is a unit of volume, so I'm going to call that V, at a temperature of 327 degrees Celsius. I see degrees Celsius, so that's temperature, but it's not in Kelvin. We convert to Kelvin by adding 273 degrees, so I'm going to add 273 degrees there, and that's going to give me a temporary conversion factor of 600 Kelvin. It goes on to say, what will the new volume be if the temperature drops to 27 degrees? So it's asking for volume, so that's going to be my V2. And it gives me another temperature, so there's T2, but again, it's in Celsius, not Kelvin. So I'm going to add 273 to give me 300 Kelvin. So now I have volume, temperature. So we can use Charles's law, V1 over T1 equals V2 over T2. And now we plug and chug. So our first volume is 6.8 liters. Our first temperature is in Kelvin, 600 K. Our second volume we don't know, that's going to be V or V2. And our second temperature, again, needs to be in Kelvin, which we converted to 300 K. So now that we have it set up, we're going to cross multiply, or you might call it the bat and ball method. I've heard people call it the butterfly method. But the point is you cross multiply, and then we'll divide by 600 K. So 6.8 times 300, if you type that into your calculator, 6.8 times 300 gives you 2040 equals 600 times V. So to get V by itself, I need to divide by 600 on both sides. Those cancel out. 2040 divided by 600 gives me a volume of 3.4, and it's liters because our first volume was in liters. Okay, now if we look at this, what did our temperatures do? Our temperature went from 600 to 300. It got cut in half. Charles' law says the volume is proportional to its temperature, so we would expect our volume to get cut in half. It went from 6.8, we calculated 3.4, so that did get cut in half, so therefore we know we did it correctly. So let's move on to problem number 2. Problem number 2 says you have a balloon in an air-conditioned room at 25 degrees Celsius. So there's your temperature. Again, not in Kelvin. Add 273 to that, and that's going to give you 298 K at a volume of 4 liters. Liters is volume. If the balloon is placed in a hot car on a summer day, its volume expands to 4.6 liters. Again, another volume. Call it V2. What is the temperature in Celsius inside the car? So we're asked to solve for temperature, but they want it to be in Celsius. For these laws to work, temperature has to be in Kelvin. So we're going to have to solve the problem, get our answer in Kelvin, and then backtrack to Celsius for our final answer. The formula, since all we have is temperature and volume, again, Charles's law, V1 over T1 equals V2 over T2. Now we plug and chug. Our first volume is 4 liters. Our first temperature, we went to Kelvin, is 298 K. Our second volume went to 4.6 liters. And our second temperature, we don't know. So again, we're going to cross multiply. So we're going to go 298 times 4.6. If you type that in your calculator, that would give you an answer of 1,370.8 equals 4 times T. Divide both sides by 4, and temperature comes out to be 342.7. But that would be in Kelvin because our first temperature was in Kelvin, but they're asking us the temperature in Celsius. So how do we do this? Well, how do you normally convert to Kelvin? To convert to Kelvin, you add to 273. So let's do the opposite to convert to Celsius. So if we minus 273 from 342.7, that's going to give you an answer of 69.7 degrees Celsius. And there you go. And if you're curious, that's inside a car. That would come out in Fahrenheit to be around 157 degrees Fahrenheit, which is crazy hot, which is why you never leave pets or people inside a car on a hot summer day. Okay, so now we're going to flip to the back side of this problem, this paper, and we're going to start working on the next one, which is Gay Lussac's. So Gay Lussac's law says the pressure of a gas is directly proportional to its temperature in Kelvin. So the pressure of a gas is directly proportional to temperature. Very similar to Charles's law, except Charles's law was temperature and volume. Gay Lussac's is temperature and pressure. In fact, when you look at the formula, it pretty much looks identical, except it's P1 over T1 instead of volume equals P2 over T2. So if we look at the first example, the gas left in a used aerosol can of spray paint is at pressure of 1 atmosphere. So there's pressure at a room temperature of 25 degrees Celsius. Again, we're at temperature, but it's in Celsius, has to be in Kelvin. So how do we convert? That's right, add 273 to it. So that's going to go to 298 Kelvin for our temperature. If the can is actually thrown into a fire, because everyone knows you should never burn an aerosol can, so you wouldn't intentionally throw it into a fire, but let's say it accidentally went into a fire. They're asking, what is the internal pressure? So they're asking for pressure in PSI. Once the can reaches a temperature, there's our temperature, of 927 Celsius. So we have two things here. One, they want our pressure to be in PSI. Our first pressure is in atmospheres. So we're going to have to do a conversion at some point. And the second thing is our temperature again is in Celsius, but it always has to be in Kelvin. So add 273 to it, and that's going to give you 1200 Kelvin. So all we have is temperature and pressure, so we can use P1 over T1 equals P2 over T2. Our first pressure is 1 atm. We could convert that into PSI right away, but since 1 is an easy number to work with mathematically, we'll save that conversion till the end. So I'm going to do 1 atm over my first temperature of 298 Kelvin equals my second pressure, which we don't know, and our second temperature is 1200 Kelvin. So now we're going to cross multiply and then divide like before. So 1 times 1200 gives me 1200 equals 298 times P. So I need to divide both sides by 298. And using your calculator, 1200 divided by 298, that's going to give me a pressure of 4.03. And since our pressure was in ATM, that's going to be ATMs, but they want it to be in PSI. So we need to do a one-step conversion. We had some problems like this last week. So I'm going to go 4.03 ATM, multiply, divide. The word on top goes on the bottom. What are we trying to get to? We're trying to get to PSI. So I'm going to put PSI on top. And what were those conversions? So PSI was 14.7 and ATM is 1. And again, these are in your notes from last week, and I'll put these conversions on your problems that y'all are going to turn in. I'll have those on that paper. Now ATM cancels out. 4.03 times 14.7 is going to give you an answer of 59.2 PSI. So the reason you don't throw an aerosol can into a fire is 59 pounds per square inch. That's like the pressure in a car tire, but a thin wall aerosol can, like a spray paint can or a hairspray can, can't withstand that pressure and it would explode in the fire. Okay, one last problem. The pressure in some truck tires is 65 PSI when the temperature is 300 Kelvin. If Billy Bob drives 85 miles to a small town HEB to buy some toilet paper, what is the temperature in the tire when the pressure goes to 80 PSI? So let's find our variables. 65 psi is pressure. Temperature 300 K is, there's your temperature. Hey, it's already in Kelvin. Great. We don't need to convert. We don't add 273 because we're already at Kelvin. 85 miles, we don't care about that. What is the temperature? So we're solving for temperature. When the pressure goes to 80 psi, here's another pressure. Look at our 2 units of pressure. They're the same. Great, no conversion. Look what they're asking for. They're asking for temperature, but they don't specify Celsius or Kelvin. So I would just leave it as whatever we get. Our first one is in Kelvin. This one is in Kelvin. So we can leave it as that because they're not telling us in the problem specifically what to go to. So my formula, P1 over T1 equals P2 over T2. And now all I do is plug and chug. 65 psi over 300 Kelvin equals 80 psi over, we don't know the temperature. So again, cross multiply, 300 times 80. That's going to give me an answer of 24,000 equals 65 times T. Divide both sides by 65. And temperature comes out to be around 369 Kelvin because our first temperature was in Kelvin. One thing I should point out on all these problems, your temperature has to be in Kelvin. If you say, well, hey, why don't I just leave it as Celsius? It won't matter. It will totally matter, and your answers will be completely wrong. You will not get the correct values if you don't solve these problems with the temperature in Kelvin. Okay, so now I'm going to have some problems for you to do. They're in the assignment section of the Google Classroom. Go ahead and solve those problems and then submit them via Google Classroom. Again, if you have questions, don't hesitate to log in during our office hours, Mondays and Wednesdays, 9 to 10, Monday, Wednesday morning, and 2 to 3, Monday, Wednesday afternoon.